Standing outside late at night, when the neighborhood is quiet, the Milky Way becomes visible. It hits you with that classic pale blue dot feeling, the humbling realization that you are on a tiny rock orbiting an average yellow star, and all your daily problems are entirely insignificant. We naturally find comfort in that view. The night sky feels peaceful. Images from space telescopes like Hubble capture majestic spirals that appear frozen in time. They look like paintings you could hang on a wall. But that serenity is an illusion caused by the extreme brevity of a human lifespan. Observed over 1 billion years, the universe is a demolition derby. Galaxies are violently active ecosystems that constantly tear each other apart. The universe is a massive construction site. To understand how it was built, we must look past the glowing stars and deconstruct the architecture of a galaxy from the ground up. We start with a foundational physics problem. If you take all normal matter in a galaxy, protons, neutrons, gas, stars, and calculate its total gravity, the pull is too weak to hold the structure together against the expansion of the universe. The visible galaxy should drift apart. In 1939, Horace W. Babcock mapped the Andromeda Galaxy and found that the math was broken. Basic orbital mechanics dictate that stars on the outer edges, far from the heavy center, should move slower. Instead, Babcock saw outer stars whipping around far too fast. The visible mass didn't generate enough gravity to keep them from flying off into space. There had to be an enormous amount of unseen mass, providing the extra gravity to glue the structure together. This is dark matter, a massive, invisible halo that provides a gravitational bowl for normal gas to fall into and eventually form stars. The evidence for this invisible anchor lies in the wreckage of the Bullet Cluster. During the collision, vast clouds of hot gas slammed together, stopping in the middle. But the mapped gravity kept going. The dark matter passed straight through like a ghost. Dark matter makes up 80% of a galaxy's mass. While supernovae blow normal gas around chaotically, the dark matter remains completely unfazed. Without this indifferent, unmoving foundation holding everything in place, internal stellar explosions would tear the galaxy apart. The stability required for stars to form and for life to evolve relies entirely on an invisible scaffold we can't even touch. This growth engine is cataclysmic. When galaxies fall toward each other, gravitational tides rip them apart. In colliding systems like the antenna galaxies, gravity squeezes the internal gas to trigger the birth of millions of new stars, while flinging long, chaotic streams of older stars completely out into space. Simulations run by the University of Oxford map a multi-phase timeline for these events. When two spiral galaxies meet, they often sideswipe each other on the first pass. Their momentum carries them through the initial crash, causing them to swing far apart like a pendulum before gravity reels them back in for a final coalescence. During this temporary separation phase, the galaxies settle down, the star formation slows, and they can look deceptively normal. If astronomers capture a snapshot during this exact window, they miss the collision entirely, meaning we are likely undercounting active mergers hiding in plain sight. The angle of impact dictates the entire timeline. A sideswipe leaves time for multiple bursts of star formation, separated by a quiet pause. But a direct, head-on radial merger happens fast. There is no separation phase. The galaxies slam together and instantly obliterate their delicate spiral structures. These collisions aren't just destructive endpoints. If the colliding galaxies bring enough raw gas into the wreckage, the collision acts as an engine of rebirth. As the chaos cools, leftover gas spins up and settles into a brand new spiral disk. A galaxy cannot grow indefinitely. If gravity and mergers were the only forces at play, every bit of gas in the universe would have collapsed into stars billions of years ago. Star formation is surprisingly inefficient because something pushes back against gravity and shuts the factory down. We recently caught this kill switch in action. When the James Webb Space Telescope looked into the early universe, astronomers found galaxies that appeared impossibly massive for their young age. These cosmic bodybuilders seem to be assembling stellar mass so fast that they threaten to break our standard models of cosmology. A closer analysis of the light spectrum revealed that this brightness came from rapidly feeding supermassive black holes rather than dense star clusters.
As gas swirls into a black hole's accretion disk, friction causes it to glow brighter than millions of stars combined. These young galaxies were just holding bright flashlights that blinded our instruments and inflated our mass estimates. These active black holes act as a galactic kill switch. To form a star, you need cold, dense gas. But as the supermassive black hole feeds, it launches immense jets of energy and radiation outward at nearly the speed of light. It acts as a thermostat, regulating the entire galaxy. The radiation heats the massive halo of diffuse gas surrounding the galaxy. Because the gas is kept hot, the atoms move too fast to condense and collapse. The black hole essentially points a giant blowtorch at the galaxy's food supply, preventing it from cooling down enough to rain back into the disk. By making the fuel inedible, the black hole starves the galaxy. Star formation shuts down. As the short-lived blue stars burn out, all that remains are the ancient, glowing red ones. The party ends, leaving behind a red, dead fossil. To study these mechanics, we naturally look at our own home. We rely on the Copernican principle, the assumption that the Milky Way is a standard template for how a galaxy operates. This scatterplot visualizes the Stanford Saga survey, comparing the Milky Way to 101 similar galaxies. We are a bizarre outlier. Those other 101 systems have satellite galaxies actively forming stars. But the Milky Way's dwarf satellites are completely quenched. We live in a cosmic retirement community. For reasons we are still mapping out, the Milky Way acts as a highly efficient bully, stripping the raw gas away from our smaller neighbors and leaving them dead in the water. That anomaly might be the reason we are here to observe it. If our galaxy were as violently active as the rest of the universe, with constant collisions and rampant deadly supernovae, the resulting chaos could easily sterilize a developing solar system. Our quiet, unusual neighborhood might be the exact requirement for life on Earth to survive long enough to look up.